So let me start. So I promised that I forgot my glasses, so you will see me reading from the distance. Okay, so I promised I would generalize everything I said before to the case in which we have we do something in between. So we either time evolve with a circuit, or we have measurements, or we have whatever we want. So in order to do that, let me just go back to something we said. P of W, the probability to do a certain work in this, with our understanding of what is work here. So it's thermally isolated system, and you're essentially measuring energy, two-point energy statistics, initial and final energy measurement. So this is defined as the sum over n and m of the probability to measure the eigenvalue n in the initial measurement. Okay, let me do it differently. No.
You need to switch to pen.
P I N, okay, then P F M N. So this is the probability to measure the eigenstate M of the energy, of the final energy, provided you measure N in the initial measurement, and delta W minus E M final minus E N initial. So that's what we have. No. Okay. So now the question is, in general, if I want to define what I'm doing, I just have to tell you what are these two probabilities, right? So if I do, for example, if I keep measuring the initial energy in which the initial state is measured according to, is distributed according to a Gibbs distribution, this guy here is always going to be e to the minus beta En initial divided by Z initial, right? Now, all the information about what I am doing between the initial energy measurement and the final energy measurement is sitting in this conditional probability, right? So, and in particular, if here, I'm doing, so what I assume I would be doing, I was doing before, so just some evolution, some unitary evolution with an initial and a final energy measurement, I would get psi f u tf ti psi I. Now, of course, this is a time-ordered exponential if the evolution is due to an Hamiltonian to which I'm changing a parameter. If the evolution is due to something else, for example, I have some gates and a circuit and a digital simulator or whatever, here I will have those gates. Okay, so it's a unitary operator and nothing else. Now, the real question is, what happens if I make some measurement in between? Now, if I make some measurement, the point is that in between so make a measurement. So if I make a measurement that is represented by a set of Krauss operators, so operators M of R are the possible outcomes. They are taken from a discrete set, and I have sum over R, MR, m dagger of r. No, the other way around. Equal to 1. Then of course, in between this initial energy measurement and the final energy measurement, I will have the measurement of some other quantity represented by these Krauss operators that will give me a certain outcome. So I can ask myself, for example, what is the probability? Instead of having this quantity here, I will have the probability to measure in the final energy m, provided I measured r and n in the previous measurements. Right? Is it clear? Okay? So is it clear what is going on here? So I do an initial energy measurement, then I measure my quantity r, I get an outcome r, and then provided I have these two outcomes, I will have a certain measurement of the final energy. But this is not the quantity that will be sitting here, right? The quantity that will be sitting here, P f of m n, is equal to the sum over all possible outcomes r of the probability to have a certain outcome r, provided you measured n in the initial measurement, times the probability to measure f, m, r, and n. Okay? Clear? Yes?
What kind of measurement are we talking about?
Anything.
This is all in the many-body eigenstate basis, right?
No. So the initial and final measurement are done with respect to some Hamiltonians, H initial and H final. And with respect to the eigenstate basis of those two Hamiltonians. So when I write m and n, m is the index of the final eigenstates, n is the index of the initial eigenstates. Okay? Clear?
Yes, and we are measuring the total energy.
You're measuring the total energy, yes. As we did before, as we did this morning.
Okay, now I'm not an expert on this, but isn't that something which is not accessible in experiments usually?
Yes, but you can, okay, it is true. It is, what you're saying is true. You cannot measure the, well, typically it's complicated to measure the total energy unless you have, I mean, you can always measure energy differences in small systems. In big systems, it's complicated to measure total energy differences. But all of these quantities can be measured, for example, by Ramsey interference in principle. So it can be measured some way. Let's keep how feasible it is to measure it. So there are ways to measure it in practice. But now we are talking as if, we are discussing as if everything is possible, right? So in principle, it is possible to measure energy, right? It's complicated, but it's possible. So here I'm saying, let's keep the same scheme as before. So you have, this is your time, you measure energy. So let's indicate that I'm measuring energy here and here. And in between I have something, I have some evolution. And in this evolution now, I want to consider the situation in which I'm measuring something else. And this something else is R. So this is M, this is N. N is the index of the initial eigenstates, M is the index of the final eigenstates, R is some other quantity you're measuring in the middle. Okay? I'm not specifying what, because I'm just saying, okay, it's something that is represented by some Krauss operators. Who cares what it is? Okay? Right, but when you do a measurement in the middle, you will have, so if you started with n, you will have a certain probability. So if you measure the eigenstate n in the first measurement of energy, you will have a certain probability to measure r in the measurement in the middle here. And then given that result, you will have a certain probability to measure m. So you just have to concatenate conditional probabilities. That's what I'm saying, in order to measure the probability to write down the probability given a certain initial energy measurement to find the final energy measurement, to get m as final energy measurement. Okay? Clear? I hope. It's not clear. Okay. Well, I can repeat. I can try to change the formulation. Anyway, yeah, now I have to do something dangerous. Okay, good. So, no, let's do it like that. Like this. Okay. So now the question is, what is this? PFMR. Well, continuously messing up. So the probability to measure PFMR why don't you have chalks? Is equal to psi f m, and then you will have u t t f t r m r u t r t I psi I n squared divided by the probability to measure r given n, where this guy here is nothing but, well, I don't need to write it in principle, but this is nothing but psi I u dagger t r t I m dagger r m r u t r t I psi I. Okay? So this is this. Now, and this normalization here emerges because, as I told you before, when you do a measurement, after the measurement, the generalization of the projection postulate is that your new wave function, let's call it psi of r, is equal to the application of the to the application of the Krauss operator divided by the probability to measure r. So that's why you get this normalization in here. So m of r is, this m of r that is sitting here is because of this generalized projection. And the normalization is because you have a square here. So the square root becomes a first power. And this has this expression. Okay? If it's new, it's complicated. I know. I went through this before you, and I know that it's messy, it's complicated, and it's confusing. But believe me, you will understand it in 1 second. Okay. So, yes.
This PRM,
Yes.
yes, is like just the probability to find
Oh, here there.
R as far as we started from the value m, it should
Yes.
be m right there.
Yes, there should be an n. You're right. So is the probability. So this is a concatenation or convolution of conditional probabilities. So this is the probability if you measured n in the initial energy measurement to measure r in the middle measurement. And this is the probability to measure m if you measured r and n in the previous measurements. Okay? And here I forgot an n. Okay, so apologies.
I'm just curious about the formula itself. I mean, as far as this is the same object, right? The same probability to measure r if we started from n.
See,
Then I would expect that
yeah, they
we
cancel each other.
Yes, yes. I mean, I just expect that it will be some formula like this.
Yeah, absolutely.
You just.
Yeah, I'm going to do it. I'm going to do it. Don't worry. I'm just explaining things slowly, but I'm going to go through. Okay, so now, as you said, if you now, since here you have this normalization and here you have this guy, the total conditional probability PF mn is the sum over R of the absolute value squared of psi f m, and then you have u tf tr mr u tr ti psi I n squared. Okay? Because they cancel each other. Now, this is for a single measurement in the middle. Imagine that now you keep looking at your system in the middle many times. Okay? So, sorry, someone was copying?
Yes.
Okay, so apologies. So imagine now, instead of doing this single measurement in the middle, I do many measurements in the middle. I do as many as I like. So I generalize this thing to the most complicated possible case. Can I change? So I have my time and time axis. And I start from some initial time. This is my final time. And here I keep doing tons of measurements. And each measurement will give me a certain outcome. So I will have R1, R2. And if I keep doing it, I will get all the way to Rn for the nth measurement. Now, the sequence of all the outcomes of my measurements, so essentially Ri, the sequence of Ri as well as n and m, spit me out what is essentially the equivalent or the formal equivalent of a quantum trajectory. If you think about it, when you draw, if you have a tight binding model, right? And you imagine measuring position at stroboscopic intervals of time and getting outcomes. Well, you will be drawing lines like this, depending on the outcomes. So that is going to be your physical representation of a trajectory. So what I'm doing here, I'm just generalizing this concept to the most general measurement I can think of. But it's a trajectory in the space of measurements. Now, since this is a trajectory in the space of possible measurements, then the question is, how will the expression that I wrote down before generalize to this case? Well, the probability, the conditional probability to measure m given an initial measurement of of n, is going to be the sum. No, I don't like this. The hell with you. the sum over all possible trajectories, so all possible outcomes of intermediate measurements, of the probability psi fm, and then here you will have tf. I'm going to specify what this operator is in a second, rj tj, and then psi I n squared, where the operator here is nothing but the generalization of what I said before. So it is u tf t rn m rn u t n t n minus 1 m r n minus 1, etc., 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 all the way to m r1 u t1 ti. So you evolve unitarily, you apply your Krauss operator, that is the generalized projection postulate, then you evolve unitarily, apply Krauss operator, evolve unitarily, apply Krauss operator, and so on and so forth. That defines, this evolution defines your quantum trajectory, okay, in general, no matter what is in between. Good. So now that we have this beautiful formula, you can very easily figure out that if sum over rj m dagger rj m rj is equal to 1, then it is also true that the sum over all trajectories of t dagger tf ti rj tj times t tf ti rj tj is equal to the identity, right? I mean, yeah, just think about it. If you take this and the Hermitian conjugate, you will get a new dagger TFTN with the U TFTN that will give you the identity. That you will get, then you will get M dagger Rn MRN, but you're summing over all R's, and that will give you the identity because of this. And then you do it for the other one, and you get the identity, and then you have to sum over Rn minus 1, and you get another identity. And you go all the way down to the last one. So at the end, you will get the identity. Yes?
Why is the first matrix is conjugated?
Sorry?
As a number, the second n conjugated.
Let me see. You're right. This is the problem of... Okay, just a second. Okay, just a second. Just a second, because I tend to mess up on simple things. No, it's correct. It is correct. How do I do undo? There's no way.
On the right. A bit right. Bottom right. Right. It's really right. Yeah.
Undo. Okay, so it was correct. No, it is correct. I think it is correct.
It is correct. My notes is the
I think it's correct. I should be the professor, and I should, I should remember all these things, but as you get older, you get confused with the simple things. So Sorry, in particular if you don't sleep. So I think it's correct. Okay. Okay, so now we have this. We can plug it back in the expression we had before. So, no. We can go back here, plug it in back here, and then take the Fourier transform and compute the generating function, right? So we can compute the generating function. So what do we get? The generating function, z, glorified z of u, integral dw pw e to the minus I w u, comes out to be equal to the sum over all trajectories of the trace of t dagger, tf, ti, rj, tj, then e to the minus I h final of u, t, tf, ti, rj, tj, e to the I h initial of u, and then we have, we cannot do this, no, too much, e to the minus beta h initial divided by z initial. So it is something very similar to what we had before. Let me remind you that before we had here a u dagger, here a u, and of course we didn't have the sum over r because we didn't have trajectories, we didn't have intermediate measurements. So in practice here, you could think of this as the generating function for each trajectory, and then in order to obtain the full generating function, you have to sum over the individual generating functions for each individual trajectory. Okay? So now the question is, does this satisfy the Jarzynski equality? Right? It's a legitimate question. The answer is, in general, no. In general, no. And the reason is the following, that in general, I told you that I have sorry. So I told you that here I will be able to prove, well, let's forget about the indices. Sum over rj, this is equal to 1. But the other way around is not necessarily true. It is not necessarily true that sum over rj is that this is equal to 1. This is not guaranteed. And I made you the example of the photodetector, right? You remember this morning. If you detect photons, every time you detect R photons, your state collapses into the vacuum. And therefore, the dagger of that operator is not a Krauss operator anymore. So you cannot think of it as the inverse. So there are, however, some operators, Krauss operators, that satisfy the condition that it is both true that this is equal to the identity, but also the inverse is true. These operators, this condition is called the condition of unitality. A channel, okay, there is something in quantum information, that is the theory of quantum channels. If a channel satisfies this condition, is called a unital channel. Unitality. But I'm not a mathematician, so unitality is for mathematicians. What does it mean physically, this condition? It means, well, first of all, if this is true, then it is also true that sum over all trajectories Rj of T Rj, T dagger Rj is equal to the identity. Okay? But what is true, I mean, the real bottom line of this story is that if I could think of TRJ as generating a trajectory because it was time evolving forward for a certain time, my state, then measurement, Krauss operator, then time evolution, Krauss operator, time evolution, Krauss operator, and so on and so far. If this condition is satisfied, also the inverse can be thought as generating the inverse trajectory. Because I evolve with U dagger, then I apply M dagger. But M dagger is a Krauss operator because of this identity. It's just a different Krauss operator. And then I evolve again, and I measure. Evolve again, and I measure. Evolve again, and I measure. Is it clear? So, in other words, this condition is allowing me, whenever this condition is satisfied, I'm allowed to think about the inverse trajectory. Otherwise, I'm not. Okay? And if I'm allowed to think about the inverse trajectory, then I can do the following. Oh, look at this. Amazing. Two fingers. Can you see what happens?
Yeah.
Did you notice?
Is it possible to get an example of Krauss operator which is satisfying unitality but not the projector?
Yes. Well, I'll write it here. So, of course, any Hermitian operator satisfies unitality. This one, so is the standard set of operators that generates a quantum jump formalism, identity minus R over 2 plus IH delta T, and M1 delta T equal to square root of delta TC, where R is equal to C dagger C. So C here is essentially the square root of R in a sense, in an appropriate sense. So these two operators satisfy unitality, and they are, well, to be honest, that satisfy unitality to first order in delta T that is assumed to be infinitesimal. And they are kosher from that point of view. Okay? So I just write them. I'm not going to tell you the story, but for those of you who are interested, all the formalisms that generate stochastic Schrödinger equations, for example, quantum jumps or phase diffusion, all the Krauss operators that generate those equations satisfy the unitality condition. So you can apply everything I'm saying to that particular case. All right. So now what you have to do is essentially, what happened? No. Okay. So you have to go back to this, right? And do the same trick we did before. So you have to z, and you have to do z of minus I beta. Now, if you do z of minus I beta, so now I'm going to change page, what you're going to get is that z of minus I beta is equal to is equal to the trace is equal to sum over Rj, the trace of, so you will have T dagger e to the minus beta h final T, so all of this contains all the Rj's, etc., we understand that. And then here you will have the usual e to the beta h initial, e to the minus beta h initial divided by z initial. Okay? So now this goes with that, as before. And now here you can use the invariance property of the trace. But you see that if you use the invariance property of the trace, you will get TT dagger. So that's why I had to assume the unitality condition. And if I do TT dagger, I will get trace of e to the minus beta h final, then sum over Rj, T dagger, Rj, and then divided by Zi. And this is equal to Zf over Zi, equal to e to the minus beta delta f. So bottom line, if we assume unitality, so if we assume that the dagger of the operator that generates the trajectory is also generating something that we can think of as a trajectory, then we have something that that satisfies the Jarzynski equality. Okay? And it's, yes?
Sorry, why for the proving of this theorem it's not enough to just to require that actually m and dagger sum over r equals unitary operator. So it can be not a Krauss one, but the brother which will satisfy the.
You think it's enough? So here at the end, I needed this to be equal to the identity,
Yes,
right?
Yes.
So you're saying that if
sum over m and dagger.
So you're saying if sum over r, if this is equal to
1.
no, yes, of course it has to be equal to 1.
Okay, but looks like this is enough.
Yeah, sure, it is enough to, yeah.
Yeah, but we don't need that m dagger m.
No,
R
but
equals
no. This was needed for, okay, this is the definition of, okay, here we're entering.
Yeah, okay.
So a Krauss operator is, so a set of Krauss operators is a set of operators that satisfies this condition, and that's it.
So this
And
theorem will work for operators m which are not a Krauss operator but satisfy the second.
Yes, but then I have a problem with normalization of the probability distribution. Because, you see, I have to have, let's go back. So here, z of 0 is the integral of P of W, which has to be equal to 1. So if you set 0 here, well, this, unless the sum over Rj of T dagger T is equal to 1, this probability distribution is not normalized. You agree? I mean, the condition you want to fail allows me to have a normalized probability distribution.
It's not clear for me.
No, let's see. So let's put z of 0. So you agree that z of 0 has to be equal to 1, right? So then what is z of 0? Is sum over Rj of trace of T dagger T Rj e to the minus beta Hi Zi. Okay? So now what I need to, I bring this sum in here, and I need this to be equal to 1, otherwise it will not be normalized. So the forward condition is needed for normalization, the backward is needed for the Jarzynski equality. Okay? Yep. Okay, so I hope I convinced you, therefore, that for some strange reason, these Jarzynski equalities, they're there even when there is no Hamiltonian. I mean, they're there even in a very general sense, right? It's a very, I don't know. I don't know how to interpret it. Probably someone smarter than me will come up with a mystical interpretation of Jarzynski equalities, but I didn't. Yes?
Maybe the statement that it's holds without Hamiltonian can be formulated that it holds when there is this property of unitality of operation.
Yeah, absolutely. Yeah, that is correct. But still, as you ask me after the lecture, what does it mean to do work, right? So can I even think of this as work? Because in the middle, in between H initial and H final, I'm doing all sorts of, I'm doing jazz. So I'm doing everything, right? So.
I wanted to ask a long time ago, maybe 20 minutes ago, but when we do measurements, what about some loss of information, like of the...
Oh, that is a very good question. You see, the fact that I'm summing over Rj means that I'm not losing information. If I would not sum over Rj, right? If I would not sum over all trajectories, but consider individually, well, let's go back. Individually, this guy here, which is, you can think of this as the, no, sorry, I used a different notation. You can think of this as being the generating function of the individual trajectory. So if you would look at this and take minus I beta, of course you will not get anything close to the Jarzynski equality. Why? Because you're losing information. Why you're losing information? Because there are other trajectories. And when you have many measurements in between, you have exponentially many possible trajectories, because that's obvious in the number of measurements that you're making. And when you pick only one of them, you're losing flux of information flux. So it is indeed true.
But if we have entanglement, it's also will be not destroyed.
Entanglement, I don't think it plays a, I don't see how it plays a major role in this story. Maybe you can come up with something, but
About pure systems, right?
no. Up to so all this story is about mixed states. First of all, right? For pure system, now we will come to pure systems, but everything now is about mixed states. Right. So plus. Good. So now that I told you this story, it's time to do something practical. First of all, So first of all, the question is, what can we expect from work statistics when we change a parameter everywhere, for example, in space in a big system, in a system in the thermodynamic limit? Do you think you will get something interesting? My face should suggest. Will you get something interesting? Of course not. Why not? Because work is an extensive quantity, right? And if you do it on a big system, then because it's extensive, you should expect the central limit theorem to kill all the fluctuations, right? So you will have a certain average work that is extensive and then fluctuations that scale like 1 over square root of n. Now, there is a curious and systematic way to see this, which is the following. Imagine, so I told you that, imagine that we do a quench starting from a pure state, from the ground state of a given Hamiltonian. So in that case, my generating function is going to have the following expression. Is going to be psi naught e to the minus, so I repeat, I'm doing a quench, so it means that I'm changing my parameter abruptly. So u, the u that I had there is 1, is the identity. It's like in the sudden approximation in quantum mechanics, okay? So in that case, I will get u minus I h final of u, and then e to the I h initial of u psi naught. I hope it's, I really do not remember. Yes. Okay. Now, of course, I mean, since this is the ground state of the initial Hamiltonian, I can take it out. It's just a phase factor. E to the I E naught lambda initial, and then I will have psi naught e to the minus I h final u psi naught. So you see that up to a phase factor, this is an object that has a name. You have ever seen it? It's the survival probability in quantum mechanics or whatever. Fidelity. It has many names. You essentially start with a state, you evolve it with an Hamiltonian for which is not an eigenstate, and you compute how much it survived of it. Now, the reason I call this Z is that this is also can be thought of as a partition function. How many of you are familiar with the quantum to classical correspondence in statistical mechanics? No? No, because if you're not familiar, I think I will have to explain a few things. Well, how many of you are familiar with the quantum Ising model? Quantum Ising chain? Almost all, close to everybody. Okay, so let me make a statement. If I take the two-dimensional Ising model, classical Ising model, so sigma is up and down, and these are classical variables. And I take it, let's say, on a square lattice in 2 dimensions. So what I have is a certain number of rows, m and n. So what is possible to prove, and this is, Undo. Undo. Where is undo? No. Yes. What is possible to prove is that the partition function of this model can be written as the trace of v to the power m, where v is called the transfer matrix. Okay? So this is a very simple elementary technique of statistical mechanics. If you're not familiar with it, you can read it in all books of StatMech. Mussardo is the one I like the most, simply because it's called the quantum statistical field theory, so it's not really StatMech. Or Wang. I'm not sure you can find it in Landau-Lifshitz. I don't know. I never read StatMech Landau-Lifshitz. So if this is true, if you have periodic boundary condition in this direction. If you don't have periodic boundary condition in this direction, then this with open boundary conditions is equal to psi naught v to the m psi naught, where these psi naught are some states, some vectors that represent the boundary conditions at the two boundaries of your system, right? So you can think of, well, you can do this in this direction, in that direction is the same, it's always the same. Now, the quantum to classical correspondence works in the following way. For certain systems, not for all systems, but for certain systems, the transfer matrix can be written as the exponential up to a number of a quantum Hamiltonian. Now, what is the dimension of the transfer matrix? The transfer matrix is connecting all configurations of, let's say, a row to other configurations of a row. So it's a matrix that has dimension 2 to the m times 2 to the m, right? Now, the quantum Hamiltonian, therefore, has to have the same dimension. And you see immediately that this Hamiltonian here, if you have a two-dimensional system, is going to describe a one-dimensional quantum system. In particular, what you can read in this book that is very nice is that, well, you know, this is in the introductory chapters. This is a book about conformal field theory and integrable systems. But what you can read in one of the introductory chapters is that, for example, for the two-dimensional Ising chain, the quantum correspondent is the one-dimensional quantum Ising chain. Okay? So the fact that I don't know, probably you know that the two-dimensional Ising model is integrable, was solved by Bethe-Ansatz by Onsager. And what is behind this is the fact, if you want, that the two-dimensional, the one-dimensional quantum Ising chain can be solved exactly by Jordan-Wigner transformation and using free Majorana fermions. Okay? Yes?
Exactly two dimensions are corresponding to one dimensions?
Well, so two-dimension classical corresponds to one-dimension quantum through this mapping. Okay? Now, the reason I've shown you this, and here I'm becoming, you know, it's more, since not all of you are familiar with the subject, I will try to be very vague, but try to give at least an appropriate impression of what is going on. So, since Z of U as this expression essentially up to a phase factor, so if you imagine that, let's say that psi final is a quantum Ising model, okay? So we are allowed to do that. So if this is equal to this, in a transverse field. So this model has a quantum phase transition at h equal 1 between a paramagnetic and a ferromagnetic phase, which correspond to the two-dimensional phase transition between paramagnet and ferromagnet. Now you see that if I do now z of minus IR, I get psi naught e to the minus h fr psi naught, and this is going to be the partition function of the two-dimensional easy model on a cylinder if I take periodic boundary condition for the Ising chain of thickness r. So this is how you use the quantum to classical correspondence. Now, why it is useful? Because the moment I tell you that this is equal to a partition function, you don't even have to think about the problem anymore. Because you know that this is going to be equal to e to the minus beta times a certain free energy, the free energy of this particular system. And the free energy is going to have three contributions. The three contributions will be characterized by how they scale with R. One contribution is going to come from all the spins sitting in the bulk. So it's going to be linear in R. So it's going to be F bulk times the circumference, let's call it L, times R. So this is essentially the area of the cylinder, and this is the bulk free energy density. Then you're going to have two contributions to the free energy from the spins that come, now I learned it, from the boundary. So sitting here and here. And these two guys will give me two F boundary times L. And then there is going to be a third contribution to the free energy that comes from the fact that in general, if you take these two boundaries and you start moving them, you will have an interaction between the spins that sit in the boundary that is mediated by spins that sit in the bulk. It's similar to the Casimir effect. You're all familiar with the Casimir effect, right? So Casimir effect in electrodynamics. So you can have something similar for statistical systems. And this is going to go like, plus e to the minus beta, undo, e to the minus r over xi, some constants, and r to the power eta. So this is the Casimir effect. In general, this interaction is cut off by the correlation length, but in practice, if the bulk is critical, you will have a power law interaction between the two boundaries. Anyway, yes?
I'm just a little bit lost. So where does this term comes from? I mean, of course, it's analogous to Casimir effect.
Well, first of all, it doesn't come from anything but from a description. So I'm not calculating anything at the moment. I'm just describing to you what are the various contributions you can expect to the free energy from this system.
It's like
Right?
a quantum system that corresponds.
No, it's not a quantum system. This is a classical system. And nothing else. Anyway, so cutting the story short, because I want to do something that is more connected to everybody here. Let me just mention that if you use this and now remember that R is equal to minus I times U, then you will be able to figure out that your generating function has indeed the properties of the I mean, as the, this central limit theory property. I mean, the fact that the fluctuation, the average is centered around a certain value and the fluctuations scale like 1 over square root of r. So you don't need to do any calculation in that particular case. So then the question is, when is it interesting to compute work statistics for a quantum systems and even for a classical system? Because to compute work statistics for the lifting of a table or of a chair is a waste of time because of the same reason. This is a macroscopic system. Fluctuations, if present, will scale like 1 over square root of the number of molecules that make your chair. So in general, you can think of having something interesting either for mesoscopic systems, so for systems that are made up of a number of particles that is not exceedingly large, or if you have a quantum system, if you are doing something local. For example, you think of taking your Ising chain and you think of changing the transverse field in one position. For example, I don't know, from H initial to some H final. And you ask yourself, okay, how much work am I doing on the system? What are the properties, etc., etc., etc. Now, to show you that you can get something interesting in this situation, let me take a standard problem in condensed matter physics. You asked me before, you told me before that it's very complicated to measure energies, right? It was actually done 50 years ago. So now I'm going to show you how. So, but before, let me ask you a question. So imagine that I have, okay, I'm here, we are at the level of the spherical cow. I don't know if you know the joke, but so this is a container, right, a spherical container, and I imagine that is full with n fermions. Let's say at 0 temperature, right? N fermions at 0 temperature. And now, at a certain time, I turn on a very tiny potential barrier in the middle of this container. So I take a potential, I don't know, V of x, which is, I don't know, lambda delta of x. Something very tiny. If you don't like a delta function, put something else, a Gaussian. So before putting this guy at t equal to 0, putting on this potential, what I get is a ground state of my set of fermions. Okay? After I put the potential, I have a new ground state of the set of fermions, psi 1. So my question is, what is the overlap between psi 0 and psi 1? In particular, I'm interested in this quantity in the limit where the number of fermions n goes to infinity. So what is the result? Okay. Any other opinion? So I usually give 3 options. 1, 0, let's say 4 options. I, and the third is pi. So what is the result?
Is it Rashford analytical test?
Yeah, of course it is. Yes. What is it? So 2 people know the answer. I know that 2 people know the answer. But then I want to know the opinion of others. because it's an interesting problem, right? It's very, very simple, and it's very interesting. Don't be shy. At CISA, many people say pi. No, I'm joking, you're recording me. So obviously it's not pi, right? So what is it?
Like 0.7.
If there are 4 answers, does it mean that there is a correct answer on this 4?
Yeah, there is a correct answer. But you have to think why it is the correct answer. Right? It's not enough to say, look, I mean, we are not in the casino, right? You have to tell me the correct answer, but also to think about why it is the correct answer. So, naively, I would say, I'm doing something very little, right? Very tiny to my system. Right? I mean, naively. But the problem is that there is this limit. So doing something tiny in the limit and going to infinity.
And the box is fixed.
Sorry?
The box, the container.
The container
Is fixed.
is fixed, yes.
And then also go into-
Yeah. So the container is fixed. So let's say that you had n particles, and let's forget about symmetrization, anti-symmetrization, complications, right? So if you have n particles, each, right, you're changing slightly your potential, your new wave functions will have an overlap with the old wave function that will be in absolute value slightly smaller than 1. Correct? Correct, right? Because you're changing, the wave function is going to slightly change. But then you're multiplying n of these slightly changed wave functions, and you're taking the limit of n going to infinity. So when you take a number that is smaller than 1 and you multiply it n times and n goes to infinity, what do you get? 0. You get 0. And this is called, it's a very nice, interesting phenomenon, very important in condensed matter physics, that has a name, is called orthogonality catastrophe. Which is a good name. So now when people complain that we call quantities the magic, I tell them, well, 50 years ago they called it the catastrophe. So you put you turn on a tiny potential in the middle of a bunch of fermions, and you have an orthogonality catastrophe. The new ground state is orthogonal in the limit of n going to infinity to the old ground state. Does this have some consequences? Well, yes. In particular, it was the experiment to see this sort of phenomenon. I mean, the first person to think about this was Phil Anderson. I don't know if you ever heard this name. He's a super important person in condensed matter physics. He's the guy who invented localization, invented the orthogonality catastrophe, invented many, many things. So the story goes as follows. There were some experiments that did the following. Take a material that has a partially filled conduction band. Right, so this is my representation of the conduction band. So is the conduction band, and then it has some deep impurity levels, right, which are filled by electrons. And then what experimentalists were doing were they were shining some X-ray radiation on this system. And what the X-ray radiation is doing is kicking these electrons off these levels. Now, in practice, they are going into the conduction band. Let me assume for simplicity that they are really kicked out of the system. So, they're shot in the air. It's not what happens in reality in the experiment. Now, in this case, what happens is that this electron is gone and leaves behind a hole, right? So the hole, I can represent it as a potential that is seen by these conduction electrons as an impurity potential, exactly as in the previous experiment that I was mentioning. Now, in practice then, if I want to describe this situation, I have an Hamiltonian that is free electrons. So how did I write it here? Oh, I wrote it in second quantization. So I have an Hamiltonian that is free electrons. And then what happens is that at a certain time, I turn on, time t equals 0, I turn on a potential barrier. So my new Hamiltonian becomes h naught plus integral dx psi x vx psi x, where v of x can be, for example, a delta function, lambda delta of x. Now, if you think about it, what is the energy that is needed to turn the knob and turn on the potential barrier here? What is the work that is done on the system in order to turn on the potential barrier? Well, the probability distribution is essentially going to be related to the absorption spectrum of X-rays that experimentalists are shining on these systems, right? So the probability distribution of the work is going to be, well, it's going to have the expression that I wrote down before, but I can interpret it practically as the absorption spectrum of X-ray radiation. So it is true that measuring energies, globally energies, is complicated, but if I'm doing something local, then, if I turn the knob by some optical means, for example, the absorption spectrum will give me information about energy statistics. All right, so now it's an interesting calculation to compute the work distribution or the absorption spectrum in this case. It's a standard, yes?
Can you say that to get potential we need to shine a photon, because photon will be absorbed and then potential will be created?
Yeah.
And we know just that with all energies above some threshold, it will be the result of such process. So the distribution is just theta function?
No, it's not theta function. So if you compute the work probability distribution, you're going to get something like this. P of W, this is the threshold, I don't know, WC. And you're going to have a power law singularity. It's not a theta function. So it is true that it's going to be finite only beyond a certain threshold, but it's not going to be behave as a theta function, and the reason is exactly the orthogonality catastrophe. So essentially, when you shine light, the system tries to readjust to the new potential by generating a cascade of of particle excitations, and this cascade of particle excitations generates this singularity. All right, so let me, since we have roughly 10 minutes, 15 minutes, let me very quickly tell you how to do this calculation of the work distribution in this case. It's an interesting calculation. It's not unlike what I told you before that was relatively new. This is a standard problem in condensed matter physics. So you can find, for example, information about it in Mahan. Was solved exactly by Nozière and De Dominicis. And that's it. So this is roughly, and it can be done also by bosonization if some of you are interested in it. It's a very old problem that was beaten to death. So it's interesting to know how to compute things, but it's not something that you can use for modern research. So anyway, it's instructive. So what is Z of U? Z of U is, no, please, e to the I h naught of u, e to the minus I h naught plus v of u. And now, well, if you look at this, you immediately think of going into the interaction representation, right? And writing this as a time-ordered exponential of minus I integral 0 u du prime vu prime. Where vu prime means that here I'm evolving with h naught. And now, whenever you see the average of an exponential of something, what is the first thing you can think of? The first type of calculation that comes to your mind? Expand. How? Expand how? No, that's correct, but how? There are two ways to expand an exponential. You brutally expand it, or you re-exponentiate it. So which way you would go? No. No. So whenever you see something of that type in statistical mechanics in any possible field, the thing you should think of is not brutal expansion, but is a cumulant expansion. So cumulant expansion means that stuff becomes exponential of minus I integral 0 u u prime b u prime connected minus 1/2 integral 0 u dt1 dt2 time ordered b t1 b t2 connected plus higher order terms. So how do you prove this? You do the brutal expansion, then you take the log, then you expand the log, and then you re-exponentiate. And then you get the cumulant expansion. Okay? So expand brutally, take the log, expand the log, re-exponentiate. And that is called a cumulant expansion. Now it's very useful because at this point life becomes simple. you can compute all these terms. Since here the time evolution is done with a non-interacting Hamiltonian, you can compute all these terms which are connected correlations using Wick theorem. So this one is straightforward. This will give you just a constant. So this is V of u is, where do we have it? Lambda over 2, lambda over L, sum over K, C dagger, K, C dagger K, C K prime, T. You see that when I take the average, since it's the average with respect to the non-interacting Hamiltonian, I will get a delta K prime. All the time dependence will be gone because this guy's, the time dependence of these guys is and therefore, yeah, you get just a number. So from the first term there, we will get, the file is too big already. From the first term there, we will get a number, e to the minus I e naught u. And then we have the second one, e to the minus 1/2 integral 0 u d u1 d u2 time ordered exponential v u1 v u2 c. Okay, so now I have to compute the second term.
Sorry?
Yes?
What is the difference compared to typical Feynman diagrams? Because it was exactly the same.
It is the same. This is the expansion that you do when you want to compute the partition function. So I'm doing it, the difference between partition function and this story is that here I have I u, and for the partition function we'll have minus beta u, minus beta h. But it's exactly the same story.
Because you asked which diagrams, and you answered Feynman, and you said it's not.
You want me to draw diagrams?
No. Just exactly
I
Feynman
can, you know, but these are not beautiful diagrams. You will not see anything spectacular. I can, you know, it's a second order perturbation expansion, so. Okay, so now what you have to do is you insert this expression in here and you take pairwise contractions. Okay, you take all possible contractions. So it's up to you to enjoy yourself taking contractions, and what you will get is this F2 of u, where F, no, don't do this, please.
You accidentally touched the button share.
I didn't touch anything. Anything I touched. He touched himself. So this is that term, which is 2 lambda squared integral 0, a cutoff, the omega, r of omega, 1 over omega squared, 1 minus e to the minus I omega u. Okay, so I'm not doing the calculation. I'm just, you know, when I did my course on condensed matter physics, my teacher was explaining at the backboard the way I'm explaining this calculation. So he was not explaining anything. He was just writing some formulas that were exactly the formulas that you had to get when you do the calculation yourself. Okay? So you are supposed to, if you're interested, to repeat this calculation, and you will cast this term in this form, where r of omega, turns out to be the following expression, if the guy wants to work, is equal to 1 over L squared sum over k prime, n of k, 1 minus n k prime, times delta of omega minus epsilon k minus epsilon of k prime. What is this object here? This is the density of particle Hall excitations. You see, I have a particle because it has to be occupied. I have a hole, it's empty, and this is the energy difference. So it's the energy density of particle Hall excitations. I leave it to yourself to convince, I leave it to you to convince yourself that this goes like, when omega goes to 0, as omega divided by 2 pi the Fermi velocity for a standard Fermi gas. So it's linear in the frequency. Why it is crucial that it's linear in the frequency? It is crucial because you see that for small omega, this linearity here kills an exponent down here, and you get a 1 over omega. And a 1 over omega is a dangerous situation because it's a logarithmic singularity. Now, logarithmic singularities you will get everywhere in condensed matter physics. If you keep studying problems in condensed matter, you will get it here, you will get it in the Kund effect that is related to this, you will get it everywhere. But the point is that they signal the presence of some interesting phenomenon typically. And the interesting phenomenon here is the orthogonality catastrophe. So anyway, if you plug that expression in here, you will get that this is roughly 2 lambda squared, 2 pi v Fermi squared. Please, integral 0 lambda d omega 1 over omega 1 minus e to the minus I omega t. And you see that here, this singularity is cut off by 1 over time, roughly speaking, because if you start expanding the exponential, you see that the first term will kill this, but then, then you will need higher orders, and you're doomed. So the result of this integral is approximately 2 lambda squared, 2 pi v Fermi squared, why you don't want to work? Log of 1 plus I lambda t. Okay. Now, you take this expression, you plug it back in here, and you get that z of u I don't know why is equal to e to the minus I e naught of u divided by 1 plus I lambda t times g, where g is lambda squared.
So what is the capital lambda and the t?
Why is the, what is t? Sorry, I made a, this is because I'm tired. So this should be, you're right. I omega u should be a u, not a t. Okay? This is a u, is not a t. And what is lambda? Lambda was, you're right, was this was the strength of the potential that I'm turning on. Lambda delta x.
Yeah, but it's a capital lambda in the.
Oh, the capital lambda is a cutoff, is an ultraviolet cutoff.
Oh, I thought this was, okay.
Sorry, I didn't even mention it. But it was not some extrapolation. It's just an ultraviolet cutoff that you have to put. Otherwise, here everything will blow up. The reason you have to put it is that when I compute this, I'm linearizing at small omega, but then I'm assuming that it stays like that forever. So I have to put an ultraviolet cutoff to kill it somewhere.
Well, we can't neglect one in comparison with the lambda u.
Sorry?
One we can't neglect one under the logarithm in comparison with the lambda u.
Well, you can. I mean, it just depends on when you invert this where you start the branch cut. So
Okay, so this parameter can be arbitrary.
yeah.
Okay.
So, I mean, the thing is that no matter what you put in here, when you invert this P of W, then you will get a theta function, W minus E naught, and then in terms of this variable, you will get exponential of minus W tilde over lambda squared divided by W tilde over lambda 1 minus G divided by lambda. So it's a power law singularity, exactly as the go up. Please. Okay. Now, what is interesting about this problem are a couple of things. First of all, as I told you, it's a problem that can be solved exactly. And here I didn't solve it exactly. I did just a straightforward cumulant expansion up to second order. If you do the calculation exactly, it can be done either in one dimension using bosonization, and that was done by Schottke and Schottke. I hope it, Schottke. Well, Schottke, the two brothers, so the second power. And it was done by Noziere de Dominicis with Feynman diagrams. You will get the same result. The only difference is what is G. So instead of this G equal to lambda squared, you will get delta over pi squared, where delta is the scattering phase shift of your of the S wave scattering of the impurity, and nothing else for spherical symmetry. Everything else is follows. So this is a nice calculation that shows you some elements of non-triviality for these work distributions, and is interesting because it tells you that, while generically for an extended system you can think that, well, all of this is not needed. For small systems, or when you're doing things locally, even measurements locally, you can think of getting some interesting results. And yeah, so I think that's it for today. Next time we will do entropy. I will define what is entropy, and this is the last thing we will do for thermodynamics. And then we will be talking about Keeble-Zurek, generalized Gibson-Sangbo, and ETH. Okay? Good.